All right. Hello, class. Um, Good afternoon. Happy Cinco de Mayo. Um, I got my apron on. I'm going to be grilling later today. I've got the carne asada marinating right now. I'm going to be making some guacamole, making some salsa. I was going to make tomatillo salsa. I really love tomatillos, but Sprouts only had like 5 really tiny tomatillos, and I was like, well, I can't make salsa out of that. Hey, Sebastian. Hey, Matthew. Um, let's see what else is going on. There's going to be no Discord today because I'm gonna start cooking right after this. Um, Let me take a look at what we're going to learn after the AP exam. So I sent out a straw poll yesterday, and thank you to those of you who filled it out. It looks like the overwhelming majority would like to learn about astrophysics. So after next week, we will be learning astrophysics. And I don't know how long that'll take, but once we're done with that, I might decide to teach you guys something else. I don't know. Hello, Ella. Hello, Elena. Salutations to you as well. All right, so we're moving on to momentum today, reviewing some momentum. And so I'm going to be doing some workbook problems from the momentum section of the workbook. So we have a scenario. 2 different boxes are pushed from rest on a frictionless surface for a time t with differing forces. Identify the box system by circling the object. I'm not going to do that. The dots below represent the 2 boxes. Draw a free body diagram showing and labeling the forces exerted on each box. Draw the relative lengths of all vectors to reflect the relative magnitudes of the forces. So, well, the right box experiences a force F. So I'm going to make that force 3 boxes long. Okay? Notice how the box number 1 experiences a force 3F. So when it says draw the relative lengths of all vectors to reflect the relative magnitudes of the forces, they mean that if one of the boxes gets F and the other one gets 3F, you better draw the other one 3 times as long. So I'm drawing that with a length of 9. Okay? Then, of course, we also have a weight force for each of them. And notice how it says that box number 2 has twice the mass. So it better have twice as big a weight force. You get what I'm saying? So this weight force, it looks like, is, I don't know, 1, 2, 3, 4, 5, 6. So this one better have a weight force that's only 3 boxes long. Okay? And then we also have normal forces, which go in the opposite direction from the floor. Should be equal and opposite to the weight force. Try to move this. Oh my gosh. Just want to grab the arrow. Something like that. 3 boxes. And then this one, 6 boxes. Something like that. So those are equal and opposite. All right. So now it says the forces that are external to the system. So I don't even see where it says what the system is. But if that's why that's irritating. But if the system equals the box and nothing else, the external forces are all of them. Now, why do I say that? I say that because the applied force is coming from the person who is not part of the system. Gravity is coming from the Earth, which is not part of the system. And normal force is also coming from the surface of the Earth, which is not part of the system. So, okay, looks like Matthew asked a question. Will the AP exam be single topic questions or will they combine multiple topics? I would expect that you can see at least one question, I would say probably is going to mix things. So, and what we're going to do next week, in the first 3 days of next week before the AP exam, is we'll actually do the free response questions from past AP exams. So you'll get a feel for that, what it's like when it mixes them. Okay. But yeah, it's fairly common to see maybe like circular motion and gravitation put together. It's common to see momentum and energy put together. It's common to see energy and projectile motion put together. So there's different combos that tend to go together. Sketch a graph of the net external force versus time for each box on the same axis by using 2 different colors and providing a key. I'm not going to use 2 different colors. That's too complicated. But what I can see, by the way, notice how it says frictionless. So I don't need to include friction in either of these free body diagrams. However, and we can also see that weight force and normal force are canceling each other. So the net external force is simply the applied force in this case. So one of them should be, so the external force versus time is just that. And the other one is going to be 3 times the force. So, I don't know, something, I'm just approximating here, but 3 times the height. All right? That looks like more than 3 to me, maybe right there. Okay? Use the equation for the area of a rectangle. Write 2 equations, one with words and one with units. For the area of the rectangle, okay, so you might recall, I'm just going to use this. So you might recall that the area under an FT graph is called impulse. The impulse due to the net force is equal to the change in momentum of the object. Important point, it's the impulse due to the net force. Okay? And you could verify that with units if you wanted to. Re-represent the data above by creating a momentum diagram for each box on the same set of axes by using 2 different colors and providing a key. A momentum diagram represents a momentum by showing the mass of the object as the width and the velocity. Okay. It looks like both boxes are starting at rest, right? I don't really understand what this is asking. So the force applied to the box is constant. Okay. The box's initial momentum is 0. This is a weird question. I don't understand what it's getting at. I'm just going to skip it. You guys won't have that luxury on the AP test, though. But I think that's poorly written. I think for the actual AP test, they definitely scrutinize the questions to make sure that they make sense. All right, part F. Is the work done on the first box while speeding up greater than, less than, or the same as the work done on the second box while speeding up? All right, so I'm going to do some equations here. The work done is equal to the force times the displacement. That's the definition of work, okay? The displacement is 1/2 mv squared, or is 1/2 a t squared. All right, that comes from a kinematics equation. The area, or sorry, the acceleration is f over m. So I have 1/2 times f times f over m times t squared. All right. So that means that the work done is equal to 1/2 f squared t squared over m. All right, so now let's compare the work done by the left system. In the left system, we have a force 3F and a mass m. So we have 1/2 times 3F quantity squared. The times are the same for both of them, and the mass is just m. So that gives us 9 times the quantity 0.5 f squared t squared over m. Okay? The work done on the right system is 1/2 times. Now, if we look at the right system, it only has a force F. It has a mass of 2m. So that means that we have 1/2 times just regular old F squared times t squared. It's the same amount of time that the force is applied for, divided by 2m. So that's equal to 0.5 times the quantity 0.5 f squared t squared over m. So you can see that the work in the left case is actually 18 times the work in the right case. See how the thing in parentheses is the same for both of them. Is the work done on the first box greater than, less than, or the same? It's greater than. Okay. If you wanted to explain this in words, I would say I just sort of I prefer to do it in terms of equations, but if you wanted to explain it in terms of words, the first box has a greater force and a smaller mass. The greater force and smaller mass mean that the displacement will be larger, okay? Greater force and greater displacement means the work will be larger, because the formula for work is force times displacement. All right, is the impulse given to the first box while speeding up greater than, less than, or the same as the impulse given by the second box? So impulse, which is denoted by J, is F times T. So if we want to know what is the impulse on the left system, notice how the times are the same for both. This one has a bigger, the left box has a bigger force, the same amount of time. Box 2 has a smaller force. Okay? So the impulse for the left is 3F times T, whereas the impulse on the right is just equal to F times T. So I would say that the impulse given to the first box is greater. Okay? So the next question I'm going to do is 140, page 140, so page 141. All right. A toy car is pushed with speed v toward a toy truck initially at rest. The car bounces back off the truck so that the car's final speed is v over 2 in the opposite direction. Consider the system to be the car and the truck. Okay. I do not get this graph at all. Class, I'm a fairly highly educated physics person. I read a lot of physics textbooks. I got a master's degree in physics, and I've never seen a velocity versus mass graph when talking about momentum before. So you know what? Screw that graph. I don't even care about it. Boom. Screw that graph. I don't care about it. But let me just solve what's going on. Okay. All right. So let me just apply the equation for conservation of momentum. If you get one of these graphs on the actual AP exam, you can punish me. Okay. Maybe one of you guys understands what this graph is talking about, and you can maybe teach the rest of the class, because I have no clue what this graph is talking about. So initial momentum equals final momentum. The initial momentum is purely carried by the cart. Okay? The smaller cart. So it has a momentum of minus mv. The final momentum, we know that the small cart recoils to the right with a velocity of v over 2. So the final momentum of the right cart is going to be positive. And then the final momentum of the other cart is going to be 3m times its final velocity. Okay? So if I wanted to solve for its final velocity, notice how the m's cancel out. So I would just have minus v equals plus v over 2 plus 3v final. Knock it off, bug! So we have minus 3/2 v equals 3v final. And then that says that minus 1/2 v equals v final. So the left cart also recoils back with speed 1/2 v. So it's kind of like this. The little car comes in, boom, hits it. They both recoil with the same speed in opposite directions. In the laboratory, a ball is dropped onto a force. What does that have to do with this? Okay. In the laboratory, a ball is dropped onto a force-sensing platform several times, each time hitting a different surface. The momentum of the ball changes by the same amount in each trial. The average scale reading is F, and the time of collision T are measured. What quantities would need to be graphed to exhibit a straight line relationship? I don't understand what that has to do with colliding cars. I'm wondering if there was like I don't know what that has to do with this. I'm just confused. I'm not going to do that. Okay. The last question I'm going to do is one on page 155. All right. I'm just going to analyze this my way because I do not understand what this is trying to do. Bad graphs. Okay, I'm just going to analyze the system. A wooden cart of mass big M is set on a horizontal section of track. The cart experiences negligible friction as it rolls. A dart of mass little m less than big M is fired with an initial speed v toward the cart, which is initially at rest. Consider the following cases. Case 1, the dart embeds itself into the cart. Case 2, the dart bounces backwards off the cart. In case 3, the dart passes through the cart. Okay, so I'm going to go to skip to the quantitative analysis. So for all of these, we're going to use initial momentum equals final momentum. So in all three cases, the initial momentum is little mv. So we're going to have little mv is p initial, and that equals p final. So I might as well just copy that. Can I copy that? It's going to be the same in all three. All right. What's different is the final momentum. So in case 1, we have a completely inelastic collision where they stick together. The dart embeds itself in the cart. So our P final is going to be V equals little m plus big M V final. So in this case, V final is going to be little mv over little m plus big M. That's V final. Okay. Case 2, the dart bounces backward off the cart. So all right, so if the dart bounces backwards, then afterwards the dart has some kind of a negative velocity. So we have minus v. Okay. So that first term is the momentum of the dart afterwards. And then we also have the momentum of the okay. So, and then that's the momentum of the cart is big M times V final. So I can solve for V final in this case. Notice how it didn't say what the bounce back velocity is, but because it didn't say what the bounce back velocity is, it must not matter what it is, right? So I'm just going to assume it's minus V. So that gives me a final velocity of 2mv over big M. All right. And then in the third case, the dart passes through the cart. So so that means that the dart has positive momentum afterwards. So let's say that the final momentum of the dart is mv, so it's unchanged, plus big M v final, where v final is the velocity of the cart. And this gives us v final equals 0. So if the dart passes through the cart, it has a very small final velocity. For simplicity, let's just assume that in all of these cases, let's just assume, because you know how it said big M is greater than little m, let's just say that big M is equal to 2 little m, just for simplicity. So what would that give for this case? That would give us v final equals v. This one would give us v final equals v over 3. So we can see that this case is the fastest. The cart ends up the fastest in the end. Okay. This cart is the second fastest afterwards, because that's v over 3. And this one is the slowest. Okay? Rank the cases in terms of the distance up the incline that the cart travels after the interaction with the dart, and explain your ranking. The faster the speed of the cart, the higher up it's going to go. That's due to energy conservation. So what we're going to have is that case 2 is the fastest. So it's going to go the farthest. Then case 1, then case 3. Okay. Trying to grab this. So like that. So I already did the reasoning because I kind of had an idea of where this question was going. All right, so I think that that is the conclusion of today's problems. And I apologize that we didn't do the velocity mass graphs. Not really sure what those are supposed to mean. Let me know if you find a resource online and you figure it out, though, because I'd be interested to learn something new. It's a little bit hard for me to figure it out like while I'm in the process of teaching it, though. I'm sure I could figure it out if I looked at the problem ahead of time, but I didn't. Okay. Have a great afternoon. Happy Cinco de Mayo, and I will talk to you tomorrow with some more review. Tomorrow we'll be reviewing simple harmonic motion.